Making Solutions is our title. I'm not having a nice handout this time, though. You're going to have to write down your questions. Are we good to go? Okay, let us proceed. Come on, click. Go ahead. Go on that. Whoops, right there. First, we're going to talk about what a standard solution is. Again, if you are tempted to stare at your phone, if you could please put your phones in your bags, that would be appreciated. Okay, so chemistry, and we're kind of heading towards stoichiometry. We're going to eventually get to doing chemical reactions in solutions. And solutions chemistry is probably the most kind of common chemistry that's done in the laboratory. Things are dissolved, we mix them, we mix acids with bases, we neutralize them, we do all kinds of different things. So knowing the concentration of a solution very precisely is a very useful thing. Somebody made the comment earlier on, when are we going to get to do like a chemistry lab other than just heating something, like we've been doing a lot of heating stuff. And close to Christmas, we'll be doing an acid-base neutralization reaction where you'll be using this equipment and solutions, and we'll be doing all of that type of stuff. And it's going to become very important that we know the concentration of the solution that we're using very precisely, all right? So when we create a solution that we know the concentration very precisely, and precisely simply means lots of significant digits, then we have what we call a standard solution. I remember when I was in university and I needed a standard solution for a particular thing that I was doing at Western, they had an actual lab technician that ran the chemical storage space, and you asked that guy for a particular solution of a certain concentration, and he would make it because his job was to make solutions and prepare chemicals, and he would tell you, there it is. He would create a standard solution, and you would know exactly what that concentration was. You can create a standard solution by starting with a solid, right? And you weigh that on a scale, and then you dissolve it in a very precise amount of water. Now, solids we can get many significant digits on. Our scales, you've seen them, they have 2 decimals. So then if we've got something like 1.25 grams, we've got 3 significant digits. I remember at university, there was a scale that had 5 significant digits. It would go 1 point something, 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 something. It was so sensitive that it had its own room, the scale did, and you went in and you closed the door and you You put it on the scale, and it had another door because any little breeze would cause those numbers to change. If a truck was driving by the laboratory, the vibration of just a vehicle driving by would cause those numbers to go up and down, and you'd have to wait until everything stabilized. So we can get masses very, very precisely. If you want to scale with 5 significant digits, though, it like costs you tens of thousands of dollars, you know, like $50,000 for a very precise scale. Our scales with the 3 digits, they're about $450 to $700. It depends on when we get it and where we get it. So they're fairly expensive as well. Now, getting precise volumes is a different thing, right? Beakers are not used for measurement. Beakers are just used for transferring. So like if I were to say you need about 80 milliliters of liquid, you know, it's about, I pour it into about 80 milliliters, I bring it back to the lab bench. If I want to measure a little more precisely, I might have you use a graduated cylinder. But these pieces of equipment up here are designed for being very precise. So these things are called volumetric flasks. They have one job. This one has one job, and that is to measure 250 milliliters of water or liquid or solution or whatever it is. It's got one mark on it, one graduation. This one's right here. They tend to be etched in the glass. I can rub my fingernail on it. So when I get this filled right to that line, the bottom of the meniscus right on there, then I know I have 250 milliliters. This is only going to give it to me to the closest milliliter. That's 3 significant digits, 250. Usually they give me a little more information. This one says 500 milliliters, and then it says plus or minus 0.2. So the error is in the first decimal. So again, that's 3 significant digits, 500, exactly 500. You can even get these little tiny ones. This is a 50. I've got little ones that are like 10, so that if you need to make a tiny little bit of solution, you put a little bit of solid in there, and then you get it to that spot, and then you know it. This one is 50 milliliters plus or minus 0.05. So the error is in the 0.5. That's 3 significant digits as well. 50.0. We know that to 3 significant digits. So if we use this properly, we know the volume really well, and we'll know it to at least 3 significant digits. This great big one here, and I use it quite a bit to make large volumes of acids and bases. This one's 2,000 plus or minus 0.5, which means the decimal, the error is in the first decimal. So I've got 2000. It's exactly 2,000, 4 significant digits in this. So I can get it very, very precisely. All right. I will talk about these devices when we talk about dilution. So really, there's 2 ways in which we can make solutions in a laboratory. We can start from a solid, which would be great, but then we can also dilute concentrated solutions. So the first part of this lesson is starting from a mass or a solid, and the second part of the lesson is starting from a pre-existing solution. Let's do a few questions that deal with starting from a mass. All right. Now, don't write this down. I used to get students to explain to me the proper order in which you put things together to make a solution. Now, in this class, I don't have enough time to have you sit down and make solutions, so I'm not going to make you memorize this type of thing. There's a particular way in which it's the best way to do that. I know Mrs. Murray has their class do it in the college level, grade 12. They will do these procedures and they'll make some solutions. If you continue on and you take a course that they need to make a solution, they'll tell you the order of it. But I don't get too excited about the procedural steps, so don't even bother writing that down. I will be providing you with any solutions that you'll need. Okay, let's do a few questions here, and then we will talk about dilution rather than starting with a solid. So the nice thing about this lesson right after the one we just did is, again, that we're doing questions that are very similar to what we did. And I told you guys yesterday that when the question was, what concentration or what is the concentration, to start by writing this down first. And what did I have you write down when I was asking for a concentration? What's that? C equals N over V. C equals N over V. And then you go hunting for that information. All right? Again, I'm hoping if you were here yesterday, you have a plan. I see a V. I can take care of that. And again, oh yeah, that's right. We're back to our right there. You put it right there on that piece of paper. There you go. Take your favorite. Oh, that's no fun.
Of course. You say the galaxy.
So again, once we write down C equals N over V, we can go looking for those particular values. I've got a V. What am I going to put that V in as? Someone other than Julia. Julia obviously understands what's going on here. What is it? Yep, but what I can't put in milliliters? 0.25. 0.25. Unless Julia's just giving a bunch of answers to make it look like she knows what she's doing. I'm confused. I'm not sure what it is. Okay. What do I have to do next? Yep. Grams into moles, molar mass, put it in, calculate, we're done. Excellent. Sodium chloride, that's a nice easy one. N equals, I got to write the triangle out sometimes. I can't see it in my mind for some reason. Molar mass, moles, no, grams per mole. There it is. M over mm. .75. 58.5. 58.5. 58.5 grams per mole. 58.5. Again, once you have it in your calculator from that answer, it's going to go into the second one, so you don't need to press clear. You could just press divide. So we have moles. Emma, do you have moles? 0.150. 0.150. And now this 3 digits becomes very important because we know that the 250 is to the exact 0 milliliter, 0.150 moles, liters. And what do we get? Yep. So is that the last number on your calculator? So how would we represent that as 3 significant digits? 0.6. How am I going to represent as 3 significant digits? 0.6, 0, 0, 0, 0. It means we know that information all the way down to the tenths, hundredths, thousandths. We know that because we know that that's a 0 and we know that that's a 0, and that is going to be moles per liter. Okay? All right? Again, that front 0 does not count as a significant digit. I don't even need to write that in. You could write this 0.6, it would be fine. So we need those zeros to represent the precision that comes from our volumetric flask. Let's do one more. Because again, this is very much review. We'll just do one more, and then we'll talk about what dilution is and how to calculate it. Do some examples there. So this one is a little more of a practical problem, something that I have to do if I need to create a solution for you guys. You know, the instructions I get for the lab, or when I create it, I determine a concentration I need. I'm going to put it in a 1 liter volumetric flask. And I need to calculate how much I have to weigh out in order to dissolve that and get that concentration. So the way I had you think about this is, if I'm asking for mass, what am I really looking for first? What is really essentially the same? Moles. So first I'm looking for moles. I'm looking for moles from that concentration. So again, however you're using to do that, C equals N over V, you're going to solve for moles. Now, on a significant digits kind of basis, how should I write the 1 liter if it's like a flask like this, where I know it down to the individual milliliter? In other words, I know it's exactly 1 liter all the way down to the milliliter. How should I express that 1 to 4 digits? The C is 0.550 molar, capital M, and the volume to 4 significant digits. How should I write that? No, that would be turning it into like, that would be turning it into 10,000. We still need it to be the number 1. I just need to express that I know all of the numbers, all of the decimals, down to the individual milliliter. Yep. Yeah, liters. 1.000. All right. Again, even with questions like this on the test, I'm not going to get super picky if you didn't put 1.000. But this lesson is about using equipment like this. That's the proper way to express it. And I can do this calculation. And because we did moles per liter times liters, we get N, which is moles. Notice I only keep the 3 digits because that's my least precise information. Right there, it's only got 3. Now I can get the mass. And I could roll that through. Now, this brings us to the molar mass. CuSO4. Right? Now, we talked about hydrates. And copper 2 sulfate comes as a hydrate. I have some right here. This is for an experiment with my grade 9s tomorrow. This is copper 2 sulfate pentahydrate. It's blue. If it wasn't pentahydrate, if that water, that hydrate was gone, this would be gray. All right? We would say it was anhydrous, without water. But this is pentahydrate. So when I weigh this, the waters are in there. So penta, how many? How many waters is penta? Have we got it? No? Yes? No? 5. 5 waters. If I'm doing a molar mass of this, I know that water is 18. 16 plus 2. So I would simply just do 5 times 18. And then I would do the rest. If you've already done the copper 2 sulfate, just add to it a 5 times 18. So if you get a hydrate in a question, don't get too excited about it. Just 18 times whatever. So what do we got? 4 times 16. Sulfur, 32.0. 32.0. Copper, I don't often use. Copper? 63.5. 63.5. I'll take a total when you get it. $249.5. Do we like it? 249.5? 249.5? Getting some nods? Getting not some nods? Some concerned looks? Okay. So that would change that to a 6. So that I wouldn't even hardly notice. Again, on tests, 32.1, I'm not really noticing. I don't get excited about it. Chlorine, I need a 35.5. Sitting in the middle is important, right? It does change your answer quite a bit. I'm okay if you put that as a 6 or a 5. Do we like that number other than the 0.6 or 0.5? Okay. Grams per mole. Mass is equal to molar mass times moles. 249.5 times 0.550. Are we okay? We're okay? So what do we get? What do you got for a number? Nasa, what do you got? 137.2 grams. And to 3 digits, we have a scale that would do that. I would probably weigh it out like that, but I could weigh it out as just 137, 3 digits, and that would work. I'm okay with that answer. That's good. Do we like it? Did we end up in the right spot? Okay. So like I said, the questions that we just did there are just like what we did yesterday. The only thing is I've now taught you that when we are making such a solution, we would make it in a volumetric flask, and therefore we would know our volumes really well. And if it's the right type of solid, then we could get what is called a standard solution. Okay, so the other way in which we can make solutions in the laboratory is by dilution. Don't worry, you can write that down. And don't worry about the be able to describe. Just do A, don't worry about B. So you can write that down. Don't even worry about that. That's a tell me how to make the solution type thing. I don't care about that. 1, 2, 4A, and 5A. Page 302. Again, the questions will be just like we did yesterday. Okay. And then that be able to describe is, describe to me what equipment and how you would blah, blah, blah. I'm not going to get you to do those questions. Okay, so like I said, there's a second way in which you can write this all down, and you can also define what a pipette is. All right, you can also write down what a pipette is. And then I'm going to do a little drawing on here to show you how we do the calculations. Don't worry about making a stock solution video or making from a stock solution video, because I'm going to show you how we do this. Again, those video links would be if you were away and you were watching the video, you'd fast forward through me talking here about this equipment, and then you could watch that video link, and it would show you how I would use this equipment. So yeah, I changed this note just a little bit before you came in, just so that we had a definition of what a pipette is. This is a really bad sentence. A pipette is equipment. Should say it is a piece of equipment, but you get the idea. It's a piece of equipment that measures a very small, precise volume. And a pipette is essentially a straw. And it's a glass straw with a reservoir in the middle. You can see this one's got a little bulb on it. It says right there 10. This is a smaller one. It's got a smaller little bulb in the middle, and this one says 4. And again, their job, a pipette's job, is just to do one thing, is to measure 10 milliliters. It's got one marking on it right there, all right? Just up above the bulb, there's another one with that. I've seen 100 milliliter pipettes. I've seen 50s, 20s, et cetera. We tend to use the 10 one in the lab that we're going to do when we get closer to Christmas. So many of the solutions, or many of the ways solutions come, are as what are called stock solutions. So something like hydrochloric acid, right? Hydrochloric acid is hydrogen chloride gas dissolved in water, all right? HClAq, all right? And so they can't sell me the gas and then expect me to bubble the gas in the water and make the gas dissolve. That's a hard thing to do. The second thing is that hydrogen chloride gas is phenomenally dangerous. Hydrogen chloride gas would have probably been first used as one of the first kind of chemical weapons used in World War I, right? So in your history classes, you would learn about things like mustard gas and things like that. And they're derived from, well, they have similar properties to things like hydrogen chloride. If there were to be a hydrogen chloride leak of gas, it dissolves phenomenally well in water. So if you were to inhale it, right, if you inhaled that gas, the inside of our lungs are very moist, and that gas would dissolve in the liquid or the water that's inside our lungs. That would create a very concentrated acid inside our lungs, which would cause our lungs to have a chemical burn on the inside. And just like any burn, like a rug burn you have, and it oozes and it oozes, the inside of your lungs would start to ooze, and pus would fill your lungs, and you'd start to choke, and you wouldn't be able to breathe. And then you'd drown in the fluid that was now inside your lungs that you couldn't expel, and it would be horrifically painful, and it would be terrible. If you could neutralize that gas before it got into your lungs, then you'd be safe. And in urine, there is a base, and that's why you've probably heard stories of, in World War I, they would be told to, urinate in a rag and then cover their faces, because as the acid is coming through the urine-soaked rag, it's being neutralized before it gets there. Anyway, so they don't sell me hydrogen chloride gas, let's say, because I'd probably kill everybody in the building. So what they sell me is a container of concentrated hydrochloric acid, like 36%. It's about 12 molar, right? So all of our calculations we've been dealing with are like 0.5. Like the lab that we're going to do tomorrow with the grade 9s, I'm having them use 1 molar. Yeah, that's concentrated enough. The strongest I've ever used in a laboratory with students is 6 molar. And then a few years later, we got some instructions from the safety people saying, don't do that lab anymore. 6 molar is too strong. If I get 12 molar on my skin, does it melt my skin? No, it doesn't. It's not that. Hydrochloric acid, it's strong, but it doesn't react that fast. Concentrated nitric acid will burn your skin. I have been burnt on my hands just a little bit because I noticed it with concentrated nitric acid. It reacts very quickly with the skin. So what do we have to do? I have to dilute it. I have to take it from that really strong concentrated version and make it safe for you guys to use. And when I dilute it, I have to take a very precise volume of the liquid and then ultimately dilute it in here. I'll just show you exactly how this works very quickly. I'll show you again when we get to the point where we're using it. Let's say this is my concentrated hydrochloric acid. It's not, it's just water. It's okay. I use this device here. It's called a pipette pump. Years ago, they would use their mouth. Danger, 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 in case you have a hiccup or something as you're working this machine. The pipette pump is essentially like a syringe, you know, like a syringe pump. It's got a little end on it that you can stick the little straw in. And so you draw it in, the liquid's coming up, you can see it. I go above the line. I pop it off and I put my index finger on it. So now I've got my middle finger and my thumb on the outside of the pipette, my index finger's on the top, and then I have to lift my finger up a little bit to let the liquid down. But if I lift it up too much, it goes past the line. So the best way to do it is to rotate it under my finger and carefully take the pressure off so I can controlled let it down. And I'm terrible at this because I'm not patient enough. Oh, there I've got it. The bottom of the meniscus is right on the line. I draw it up the side, make sure there's no drips hanging on it. I put it in the volumetric flask I want to put it in, and I let it drain. That's how you use a pipette. It never works that easy when you're trying to do a real laboratory, so you'll get a chance to use this. It's fun. There's a reason I'm waiting for it to drain. So it drains. You touch it off the side of the glass so that every drip comes off. And I don't know if you can see it, right? Maybe the front row can see it. There's a little bit of water left in there. See how the line's right there? These things are designed to leave that little bit of liquid in there. You don't have to push it out. So it's designed that a little bit is going to hang on to the end. Then that will be 10 plus or minus 0.04. So I know exactly that it's 0.0. That's 3 significant digits. I know that to 3 significant digits. Okay? And that's important that we know it to 3 significant digits. These pieces of equipment here are very expensive. Well, you know, something like this is probably $45, $50. Something like this is probably $30 to $40, even though it's just one little thing. And that's because precise things are expensive things, because it takes time and effort to make it properly. Okay. Let's now talk about the calculation. I am going to take a small volume of the concentrated solution. There it is. It's a small volume. It has a particular concentration of C1, the beginning volume. And I have, the beginning concentration. And I have a particular volume of V1, which I measured probably in my pipette. I am now going to take that and I'm going to dump that into a larger volume. I wouldn't use a beaker, I'd use a volumetric flask. But just for the sake of the picture, I'm now going to dump that into here, and it's going to dilute, all right? I can represent that dilution by maybe, say, 5 dots. Say I got 5 dots right there representing, say, 5 moles. And those 5 moles are in a very small volume. Now I dump it into some pure water, and those 5 moles are very spread out. Now it's much more dilute. The volume is bigger. There's less particles per liter. They're spread out. For the purposes of my calculation, we'll say that this is C2, the concentration after I dilute it. And we will say that it is now at V2, the volume after. Well, I can calculate the moles. C equals N over V. So N1 equals C1 times V1. All right? Because that's just a simple calculation from C equals N over V. I can do the same thing here. N2 is equal to C2 times V2. What's true about N1 and N2? They're the same. The moles that were in the first are the moles that's in the second. So N1 is N2. My 5 dots and my 5 dots. It's just they're spread out more. They're dilute. Which means I can create this equation here. C1 times V1 equals C2 times V2. That is the dilution equation. It's not on my equation sheet. When I built the equation sheet, there are a few things I didn't think of. That's okay. This is just a variation of C equals N over V. Now, before we use this equation, I want you to think logically. If the V increases, what happens if I make V2 really big? I pour it into lots of water. What happens to the concentration after I've added lots of water? What will happen to the C value if I make the V really big? What will happen to the concentration number when I make the volume big? Yeah, Nasa? It's going to get small. So when the V goes up, the C goes down. We talked about that when we did our quantitative error analysis. What did we call the relationship when one number goes up, the other number goes down? Yep. That's not direct. It's indirect. Direct would be this, right? This is indirect. So that's an indirect relationship. When one goes up, the other one goes down. We don't have to talk about dilution. What if I took a constant, or what if I took a weak solution and I evaporated away lots of water? In other words, what if I made the volume go down? What if I boiled off lots of water? I hope that we can see the relationship here. What's going to happen to the concentration when the volume gets really small? It's going to be good. The concentration will be high. Okay? All right? So it's an indirect relationship. Does the opposite. Let's do a few questions, and then I am done. All right, right there. Okay. Oh, I didn't talk about units. When you're done writing that down, I got to go back to the other slide and talk about units. Okay, I'll put it back on that slide in a second. I just want to talk about units. So I'm going to go back to here. Yes, I created an equation that used moles. But because I've got this equation that's a relationship, it doesn't matter what the units are as long as they're the same. So if I'm going to use milliliters on the left, I got to use milliliters on the right. If I'm going to use molarity for a concentration, I got to use molarity. But if I know a percentage concentration, I can get a percentage concentration. Doesn't matter what the units are, as long as they're the same. So, units must be the same on both sides. And when I say same, I don't mean all milliliters. I mean volume units must be the same and concentration units must be the same. So depending on what we're given. Okay. So the units must be the same. Let's go back to this. So, because there's a lot of V's and a lot of C's, I've never ever asked you guys to make sure you write down your data, right? Put your data table down. Some grade 9 teachers like that. You know, I don't even make my grade 9 to do it, right? Write the data. But because there's lots of V's and C's, I think it's useful to write the data. Now, I did say 1 before and 2 after, but it really doesn't matter. I could have used B and A for before and after. I could have used A and B for before and after. It simply means that you've got to put the right volume with the right concentration. So, what volume of this concentration? So because I encounter these first, I'm going to write V1 equals, I don't know. And because it says of that concentration, C1, is 12 molar. So I put 1s and 2s in terms of how I encounter them in the question. Needed to make 1.5 liters of 0.100 molar solution. Now I write down the equation. C1V1 equals C2V2. I stick the numbers in, I do a little dividing, and I get an answer. C1, 12 molar. V1, that's the unknown. C2, 0.100 molar. But I should put the unit in just to show you what happens to the unit numbers. I don't get too excited if you don't put the units in. And V2 is 1.5 liters. I'm hoping we've done enough math problems at this point that you know where to move things. 12 molar is going to go down below. I'm going to just write it down to show you what's happening here. 12 molar, 12 molar. Now, if we think about the units, these molarities have canceled. These molarities have canceled. The only unit I'm left with is the unit of liters. And so V1 becomes what? What do we get? Again, you can do this all in one shot. Two numbers on the top. You're going to go 0.1 times 1.5. Any number that's on the bottom, you press the divide button for, divided by 12. You can do it all in one shot. You don't need to press an equal sign. You don't need to rewrite it. Somebody have a number there? Clarissa, what have you got? How to play that game? Kara, what do you got? 0.0125 liters. How many milliliters would that be? If I needed to measure that in a volumetric flask or a pipette, what would I wouldn't measure it in a volumetric flask. How many milliliters is that? Come on, folks. This is an easy one. What do you got? Yeah, it'd be 12.5. All right, 12.5. 12.5 milliliters, maybe in a graduated cylinder. We will do two more. Oh, wait a minute. No, I don't want to do that one. Sorry, you started writing. Stop. Let's do that one. Let's do that one. Yes. Yep. With a shiny new fun video. We're going to do this exactly the same way. Even though we've got percentages, doesn't matter. They're both percentages. That's good. We couldn't do it if one was molarity and the other one was percent, but we could. And I think this is W/V. Even though hydrogen chloride is a gas, I think it's a W/V. Not that that matters. It doesn't affect anything. Again, once you are done writing it, 1 liter of 10%, they go together as ones or twos. Doesn't really matter what you pick. It doesn't affect the math. The math will be correct. And then the stock solution is that, and the question is what volume of the stock solution. So because it's first, I would go V1 is 1, and I would go C1 is 10%, and I would go C2 is 36%, and I would go V2 is, again, question mark, how much do we need if we want to make it? Again, this question is just like the last one. Even though we're making it and we need this first, it doesn't matter whether it's 1 or 2. It doesn't affect anything. C1V1, C2V2, C1 10%, V1 1 liter, C2 36%, V2, what do we need? I'm not even going to move that. If you get good at this, you don't even need to write the move. You could do this times this divided by that and be done. I don't need to see every step in a calculation, but it is nice to see your initial numbers in and then coming up with a number. What do we need?
Again with the hovering.
Just checking. See if you got an answer. Well, you weren't going to share. You going to share your answer?
No.
Who's got an answer? Who's got an answer? What do you got? Tristan? What do you got? A lot of pressure. A lot of pressure for some reason. Nasa, what do you got? Oh, now no one's going to share. 0.278 liters. 2 significant digits. I like it. 0.3. I think we would say that that's 2 significant digits. I would write that as 0.28 liters. That's what I would do. That's what Clarissa had too. Just saying. One more. One more. Yep. You could straight up round it. I know some teachers, they'll make you do that, right? They'll make you write down what's in the thing and then show the rounding. I'm not that picky. This one is a little different in that we're looking for a concentration. And it's got one little special thing. What's the issue that we have to solve for or fix before we can, ones in liters, ones in milliliters. It doesn't matter what you convert to what. Convert it to whatever you find the most convenient to convert it to. Again, 15 of 18, they go together. And again, we're looking for the C at that V. Again, I would go V1, 15 milliliters, C1, 18, there's no point there, so it's 18, 2 digits. That's a V2, 1.75 liters. I'll convert that in a second. C2 equals. What am I converting? Maddie? What's your favorite unit? Milliliters or liters? You like this in liters, so what would this be? You want to convert that to liters? Okay, what do you got? .0115. That's a 5. That's a really bad 5. That's me. 1.5. All right. Now you got it in the same unit. Way you go. Doesn't matter which one we converted. C1V1 equals C2V2. 18. 0.015. C2 is what we're looking for. And V2 is 1.75. And I'm looking for C2. And I have a little worksheet That has dilution questions on it, and the answers are on it as well. I'll hand that out in a second. Again, here the volume's getting big, so my concentration should be small. Rachel, do you have a number? What do you got? 0.2. One more digit would be great. 0.215? 0.15? 0.15? And that's in molarity. All right? Okay? I've got one little story. So, when did I tell that question? Okay. So, my wife has 2 artificial jaw joints. So she had problems with her jaw all of her life, and probably about 15, 20 years ago, they replaced one of her jaw joints with an artificial joint, and then about 10 years later, they did the other side. So the first time she had the first artificial jaw joint replaced, it was in a hospital in Toronto. She had an allergic reaction to something that they were using during surgery. So she ended up, they had to stop the surgery. Anyway, she ended up in the ICU. It was a little stressful. So I'm up in the ICU and just hanging out because she's all bandaged up. And anyway, this was in a teaching hospital. And there was this guy, and he strutted around there. He had his white jack coat on, right? His coat was on. And he had the button-down shirt that was like 3 or 4 buttons down. And he strutted around with his little clipboard, and he was going to be a doctor, all exciting stuff. And I'm sitting there just listening away, and he approaches another student doctor, like an intern, I guess. And he says to the girl, he says, I'm supposed to be giving my patient in room whatever, such and such, and he was talking about a concentration. And he says, I'm supposed to dilute it. Can you check my calculation? And I thought, are you kidding me? This is why I do this. This is why I teach this lesson. I desperately wanted to get up and just say, C1V1 equals C2V2, man. Are you kidding me? You're going to be a doctor. Getting someone to check your homework. Anyway, that's the end of my story. What's that? I should have. You're going to kill somebody. Man.